Hello and welcome to this video. In this video we're going to look at the energy levels of the atom and how they behave. So we've already looked at the nucleus of an atom and we've seen how it's all held together by the strong force, how the protons and neutrons will transfer pions between them and the quarks will transfer quarks between them to all stick together. And now we're going to zoom out a little bit and we're going to look at the energy levels of the atom. So we know the atom looks something like this. So we have our nucleus, which is very small. We said it was on the order of 10 to the minus 15 meters. And then we have energy levels, which hold electrons around it. Okay, so, and we have a limit on the amount of electrons we can hold. So we can have 2 in the very first one, 8 in the second one, and 8 in the third one, although that will change if you're doing A-level chemistry. It goes up to 10. But we're not going to worry about the capacity of these things too much. We're going to worry about the fact that each of these energy levels has a very specific energy, and that's why they're called energy levels. So we can't find a single electron between energy levels. It's not possible. Okay, so for an electron to fill an energy level or to sit inside an energy level, it has to have that specific energy. And so what we do in this section is we take a very short, a very zoomed in look at one of these energy levels, and we can draw this out. So our diagrams look something like this. Okay, where each of these lines is an energy level. Okay, I'm just going to draw 4. You can draw off to infinity if you really wanted to. Now, each of these energy levels has a number. So let's say this is the first energy level. This would be the second one. This would be the third one. This would be the fourth one, and then we get 5th, 6th, 7th, depending on how big your atom is. But even if we don't have an occupied energy level, the energy level can still exist, because the electrons, now that we're going to transfer from looking at particle physics into quantum physics, the electrons themselves can actually occupy an empty space. So the way we know electrons are there is they're somewhere in there, but we can't ever pinpoint exactly where it is. When you see all of these images or GIFs where they're talking about how the electrons orbit the atoms in perfect circles, that's not true. Okay, so we have areas in an atom where electrons could be found, but we can never pinpoint the exact position and direction of the electron at the same time. That's called Heisenberg uncertainty principle. But we do know that they're in there, so we can say for certain, once we've measured them, that there are electrons in there. Okay, so each of these things has a very specific energy. I'm going to take a few random numbers. One of them isn't going to be random. One of them you're going to see quite a lot, but the others I'm just going to choose random. So this energy here, the energy of this energy level. So this energy level, n equals 1, is what we call the ground state. Okay, the ground state is the lowest possible energy of the electron. But we could also apply this term ground state to a whole atom. So if we have all electrons as close to the nucleus as possible, we would say it's in its ground state, because we don't have any extra energy. We've got no ionization, so it has the lowest possible energy that that atom could have. So it could also be applied to the atom. But this energy of this is minus 13.6 electron volts. Okay, this is now what we refer to as the ionization energy. This value is specific to hydrogen. So the hydrogen atom has an ionization energy of minus 13.6 electron volts. But any atom that you take, if you look at the energy of its ground state, if you put in this amount of energy into the system, then all of the electrons will be ionized, or at least one of the electrons will be ionized. If you put in a multiple of this energy equal to the amount of electrons that you have, then you would ionize basically all of them, although it would get harder as you go on because you're trying to take electrons away from a positive ion. But this is what we call the ionization energy. So this is the energy required to remove an electron from an atom. Okay, and as we go up, the energy will start to increase. Okay, so we're going from negatives. So if we go closer to 0, our value is increased. So let's say this is 3.6 electron volts. Let's say this energy is minus 1.4 electron volts. And let's say this energy is minus 0.82 electron volts. These three values I've just made up. Okay, so let's assume we have an electron in the ground state. Now we know that electrons can leave the atom by absorbing energy. And the way they absorb that energy is through photons, or at least that's what we're going to look at for this. There are other ways that it could absorb that energy. It could have a collision with another atom, which is another thing we're going to look at in this quantum topic. But for the purpose of this video, it's just going to be it absorbs energy from a photon. Okay, so let me get rid of this line. And what happens is if the photon comes in, okay, so this is my photon with some energy E1, just to separate it from all of these E's. It has some energy E1, and this electron absorbs this photon. Now we're going to have a separate video looking at what photons are exactly, because they're very weird things that we're not fully understanding just yet. But a photon is essentially, you can think about it as just a ball of energy. Okay, so this ball of energy is like a packet. The electron absorbs it, so it gains more energy, and depending on the amount of energy that this photon has, it can then increase in energy level. Okay, in order for it to increase, the energy of this photon has to be either a specific difference between these two. So if I wanted to go from the first ground state to the second energy level, I would have to put in 10 electron volts, because that's the difference between 13.6 and 3.6. Okay, if I wanted to go to 1.4, I'd have to put in 12.2 electron volts worth of energy, and it would go straight up to this. If I put in an amount between 10 and 12.2, so let's say I put 11 electron volts in, it would rise up, but it would only get to about here, and it can't be in the middle of two energy levels because it can't occupy that space, and so that one won't actually cause it to increase. Okay, but so if E1 is equal to a difference in energy between two levels, the electron is what we call excited. Okay, that is the technical term. The electron gets excited, it gains more energy, it will jump up to here, and this is now an excited electron because it has more energy than it had originally. But this is also true for the atom as a whole. The atom could also be described as being excited because the atom itself as a whole has also gained this much energy. Okay, so this is excitation. So excitation is when an electron jumps up an energy level, and when it does this, it's not favorable for an atom to be in this state. It's not as stable as if it's in the ground state. So this is why most of the time in atoms you always get the electrons want to go as close to the nucleus as possible. That's why we fill up the first energy level, then the second, because it's just more stable that way. So if we've excited the atom then wants to get back down to its original energy. And so let's say we had a different electron. So this one gets ionized, or not ionized, just excited into this space. And then this electron here sees the opportunity and then is going to jump down to this space. Okay, the space that this one here has left behind, this one's going to fill. Okay, so then excited electrons will de-excite. Excited electrons de-excite, but only if they have space to go. So if we know the maximum capacity of the ground state energy level is 2 electrons. So if there was an excitation and then there was one space open, 1 electron could come down. We couldn't have more than 1 electron filling in one space. Okay, but the excited electrons de-excite, and in order to do that, we're actually losing energy. So we've gained energy to get up. So if we're going back down, we're losing energy. And we know we can't destroy energy, so the energy has to be emitted somehow. And that energy is emitted in a second photon. Okay, so this is a secondary photon. Okay, the energy of this photon will be exactly the same as the energy of this photon, because this photon has to be the difference between these two energy levels. Okay, so this will also have energy E1, because it's the energy lost is equal to the difference in energy of these two energy levels, and that has to be conserved. So we have to emit something that holds that amount of energy, and it's just easiest to emit a photon. So excited electrons de-excite, emitting a photon of energy equal to the difference between levels. Okay, so the energy released is going to be 10 electron volts. Okay, so we know we can excite it, we can de-excite it, we can also ionize it, and that's what this is. So the ionization energy is the energy required to remove an electron. So if we're talking about an ion, we're removing an electron. Now I've used this to be the ionization energy. This is the ionization energy of hydrogen, and this is the ionization energy because hydrogen only has 1 electron in its ground state, so we need to remove it from the ground state. For other atoms, we'll have electrons maybe in the 3rd energy level, and in that case, to ionize this electron, we'd only have to put in 1.4 electron volts worth of energy. Okay, so we can excite it, we can de-excite it, we can ionize it, but we still have a question as to why are all of these energies negative? Surely we can't have negative energy. We've always known energy to be scalar, and so why are all of these energies negative? Okay, and the reason is, let me just write it down here so I have more space. So why are the energies negative? This question is something you're going to cover more in A2. So this is A2 electric circuits. Not circuits, just electric fields, sorry. You're going to cover this in electric fields. But essentially, the way you can think about it is, if we've got an electron, and this is the nucleus here, so this electron is in the energy level here, and this electron we can ionize, so we can get it to leave this atom. So let's say this is like the boundary that it has to pass, so this is the outermost energy, and it can leave this atom if we put in just the right amount of energy. But if we put in just the right amount of energy, it can get to the outside and then have 0 kinetic energy, right? So we've had to add in energy. We obviously know it has to still contain mass energy, but we know that we can add in energy and make it equal to 0. So we can add energy And the result of that is that energy can become zero because it's stationary. As long as we have no excess energy to take it to go to kinetic energy. So for example, for hydrogen, if we put in exactly 13.6 electron volts of energy, it will be ionized, but then has no more energy to be able to move away from the atom. So it will exist there with zero energy. And so if we have to add in energy to get up to zero, then surely all of these energies are negative, okay? It's kind of a convention, really. So this is the definition kind of thing you'll think about it in A2 fields, but really it's convention, okay? So it's just because we have this problem that if we add in energy, we can get to zero. So we choose the convention that these are negative. And so as a general rule, potential energies can be negative, okay? So if you had gravitational potential energy, that can also be negative. But like kinetic energy, mass energy, thermal energy, these things can't be negative, okay? So potential energy can be negative now. And that's just because we can add in potential energy to something and get it up to be 0 joules of regular energy. Okay, so there is one equation that we have to know. It is gonna make maybe a little bit of sense right now, but it'll make more sense if you go and watch the photons video afterwards as well. So it's this statement here. So if the energy is equal to the difference in energy levels between the two levels, then the electron can move. Okay, so this is the same for it being excited or de-excited, and there is an equation that you can find in your formula sheet that says that HF is equal to E2 minus E1. Okay, so this is the equation for this, and HF is just the energy of a photon. Okay, energy of a photon. And E2 is the energy level that you're going to, and E1 is the energy level that you started from. It doesn't always have to be between 1 and 2, but that's just calling it like the initial and final energy levels. So it's basically, in the case that we've done here, where we've gone from n equals 1 to n equals 2, it's the difference between 13.6 and 3.6. And so then we get that has to be equal to the energy of this, and so that we can tell what the frequency of that photon is. But we'll look more at this idea that E equals HF in the photons video. So this is energy levels. We're going to use this idea a lot through quantum. This is going to be the main basis of everything that we're going to do. So hopefully this all makes sense, and thank you for watching.